This is the Lexington High School Robotics group. This is one of two groups that is there. This is the STAR. This is the device that they have built and designed and built, and they're going to talk to us tonight about what went into doing that.
First, let's all introduce ourselves. I'm Kriti Mugala. I'm a junior this year in high school. This is my third year on the team.
I'm Anhad Sani. This is my first year on the team. I'm a sophomore.
Hi, I'm Jesse, and this is my third year on the team.
I'm Arjun, also junior, also my third year on the team.
I'm Mike, I'm sophomore, it's my first year on the team.
I'm Noor, I'm a junior, this is my third year on the team.
I'm Jennifer, I'm a sophomore, and this is also my first year on the team.
I'm Neil, this is also my third year on the team.
I'm Kevin, this is my third year, and I graduated 2 days ago.
Congratulations! Welcome to the scary real world.
All right, so we're 2 Bits in a Byte. We're a robotics team that participates in the First Tech Challenge. We were founded 9 years ago at Lexington High School, and we're completely self-funded, meaning that we raise all of our own money, and we don't take anything from the school or the town. So what is FIRST? FIRST is an organization that seeks to encourage kids like us to get into STEM, and they have competitions for grades 3 through 12.
Okay, so as part of the First Tech Challenge, which is the program we compete in, we're strongly encouraged to do a lot of outreach. There's a lot of advancement opportunities in the competitions, and just a great way to spread STEM. So a few of the things we do is we try to go to a lot of local events and let kids and parents talk with them about STEM careers, and also let them drive the robots around. So recently we went to the Boston Mini Maker Fair, the local Lexington Discovery Day, and the Birthday Wishes Cakewalk, which is a charity for underprivileged kids. We also try to talk with a lot of professionals in the field. So recently we toured Ava Robotics, which is a telepresence company, Mass Robotics, and iRobot. And we got a lot of chance to talk about the careers in STEM that some of us might be interested in, especially in engineering. And another thing that we do as a big part of our outreach is just trying to teach kids robotics. So the biggest thing we do is we have a rookie program, which takes underclassmen from our high school and teaches them the basics of robotics. And we have classes with them, and then we have a competition at the end of the year. And this is a great way because to teach kids about engineering, because there is only one engineering class at our high school, and it's only for seniors. And we also started teaching started teaching at a local recreation center, Hayden, to teach elementary schoolers and middle schoolers robotics.
So this is the actual challenge. What we do is every year FTC gives us a different challenge to compete in. That's a diagram of what the field actually looks like. I'm just going to go through a little bit of the terminology that we use, because I'm sure all of us today will be using it. It'll probably get a little confusing. On the 2 corners, you'll see like the gold, or like the yellow and the silver. Those are the minerals, and they're just little wiffle balls and cubes. Then in the middle is the lander, and that's where we have to deposit those minerals into. And you can't really tell from the picture, but you have to put them into a certain side, and so 2 of the sides are only for the silver minerals, while the other 2 sides are only for the gold minerals. So this is a video of us in competition, and I'll just explain it as we go through it. So this is the autonomous section where the drivers are not controlling the robot. They were required to unhang from the lander and then put the bot on the field. And then from there, we were required to sense which one was the gold mineral and then move it from its position without moving the silver minerals.
So is the robot autonomous? It can discern between gold and non-gold?
Yeah. Yeah, and so you can really see in this video how different teams approach solving the same challenge. All the robots look really different. But yeah. All right, so in this section of the challenge, this is driver controlled. So we have 2 drivers that control the robot, and they need to get the minerals from the crater and then deposit them into the lander.
That one with the arm's pretty cool.
You can see which one is theirs on the right. That one is dropping right now.
Yeah.
It's eating them up.
Yeah, smart.
So the general idea is this is like you're dropped on a planet and you're helping with a mining operation?
Yeah, that's the story behind it. Story of
Sorry, I came in late, but how much of this challenge did you know ahead of time? Like, did you know there'd be a bucket in the middle?
Yeah, so they tell us the challenge details in like late August, and then our first competitions are generally in late December.
So they gave you the rules, like there's a bucket
Yeah,
where
yeah.
you can pick between different colors.
Yep, so they give us all the rules beforehand.
So you've got like 4 months from spec to competition?
Yeah, so the first competitions are like around 4 months in, but then our last competition this year was in March. And so we're obviously like, we keep on updating the robot in between each competition.
So when you get the specs, do you have just a bucket of parts or do you have something partially assembled by then?
So generally we start from scratch every year. I know some teams have a chassis already assembled and they'll add parts, but last year we started completely from scratch.
So how do you divide the tasks? The mechanical, people that are going to put the mechanical device together, those that are going to write the software, the app.
Yeah, so most people on the team have one thing that they mainly focus on. A majority of us do hardware. Neil and Mike do most of the software for the team. But yeah, we split it up. So we have some constraints that are put on the robot. They play a really big role in how we design our robot and the different designs that we choose to use. It must fit within an 18-inch cube. It has to be under 42 pounds. All the power has to come from a single 12-volt battery. And then we can only have 8 motors and 12 servos on the robot.
What's a servo versus a motor?
So the difference between servos and motors are these bigger actuators that you can see here. We don't have precise control over the actual angle that the motor is at, but we can control its speed and we can measure its rotations. With servos, they have a limited range of motion. They're also weaker and slower, but we can get really precise at which angle they're turning at. Okay, so this is our drivetrain. It consists of the 4 wheels and motors that drive them. This is the part of the robot that most teams will actually try and build before the competition is announced because it doesn't change a lot. One thing about this competition is that it had the elevated crater walls in each corner of the field. So those were hard to navigate over because they were a big obstacle in our way. So that's why we couldn't actually build our drivetrain ahead of time. Because we had to elevate it a couple inches off the ground to clear those walls. And we couldn't anticipate that. Okay, so for our drivetrain, we use a holonomic drive. This is a unique system of movement, which basically means that every available degree of freedom is able to be independently controlled. So what that means for driving in 2 dimensions, we have 3 available degrees of freedom. One is our x-coordinate, one is our y-coordinate, and one is the rotation that we're at. In theory, for each of these degrees of freedom, you would only need 1 motor to control them, so that's 3 motors total for the drivetrain. And there are 2 systems that accomplish this, as you can see here. The problem is that one of the major constraints in our robot is that we have to fit inside an 18-inch cube. So that means it's best for our drivetrain to be a square shape. And the problems with these ones is this one is triangular, and then that one has a motor in the middle, which is taking up valuable space. So that's why we didn't go with those. The system that we used actually consists of these specialized wheels called Mechnum wheels. So the unique thing about these wheels is that they consist of a set of tapered rollers like this. They're all mounted at a 45-degree angle. The important thing about these rollers is that they're pretty grippy. So in one axis, they can roll freely, which is the free axis, and then at a right angle to that is the restricted axis, which prevents movement. Once you combine all of those rollers and you put them on a wheel, that means that when you turn the wheel forwards, the robot actually, or the wheel moves in a diagonal vector of movement like this, and then at a right angle to that is free movement. So the main advantage of a holonomic drive is agility. We have a very limited amount of space to work with on the field, considering that there are 4 other robots and then all of the structures actually on the field. So that means we basically have to be able to turn on point and then move in any direction that we want to, like on demand. So here's a good example for that. This would be parallel parking if you have a holonomic drive. You can see it's very simple. You just reverse in and then translate at a right angle to that. And then this is parallel parking with a regular car. As you can see, it's a lot more complex. An important thing to note is that driving with a regular car, even though you can be at any location and you can rotate, the car actually has a non-holonomic drivetrain, because when you want to make a turn, you often end up moving to a different location while you're executing that turn, which obviously wouldn't work for our robot considering the space constraints.
Do you lose points in the competition if you bang into another robot?
You actually don't, but there are specific rules about how defensive you can be and how much you can like interfere with other robots. Okay, so when you combine the diagonal vectors of all 4 mechanism wheels, you can achieve basically the 6 basic motions in 2D space. So first off, the most simple one is when all the wheels are going forwards. Even though the diagonal vectors of movement for each wheel are pointing in different directions, the end result is that the whole robot moves forwards. Then by flipping the directions of 2 of the wheels, we can achieve the more complex motions. So for example, if the wheels on each corner, on 2 of the corners move in reverse, we actually translate left and right. And then in the last configuration, we can rotate in place. And then if we want to accomplish hybrid motions, like moving and turning at the same time, which you'll see in our autonomous program, we can vary the speeds of each motor and sort of blend these actions.
Do these wheels sort of assume you have a nice, clean, flat floor? What if you're in dirt or mud or?
They will not work on ideal surfaces. So actually, the surface that we're driving on is very tightly controlled. It consists of these foam tiles, as you can see there.
Okay.
Okay, so now I'm going to explain the collection wheels, which is what we use to actually pick up the minerals. So the problem was that the minerals are in the crater and they're different shapes and sizes, and we often find them closely packed in clumps. So that's why they're hard to work with. We came up with 2 solutions for this problem. The first solution we call a noodler. Basically, it consists of stiff rubber tubes that are like a rake, and it spins to intake the minerals. It also requires a ramp or a box where the minerals can be pushed into. So
like a dustbin?
Yeah, like exactly. So there were a couple problems with this, which is why we didn't actually go with it on our competition robot. First of all, the ramp or box has to be maintained at a height high enough above the floor so that it doesn't touch, and also low enough so that the minerals can easily roll into it. For our robot, because it's constantly moving around, it's hard to maintain this height, and we had problems with it catching on the floor, actually. Another thing is that while we're intaking minerals with the noodler, it creates this pushing force that's diagonal, and it works well for balls because they can roll, but the cubes often have their corner catching on the floor, which causes problems again. So our second solution is these flexible silicone wheels that you can see on the front of the robot. The system consists of 2 wheels that rotate in opposite directions that actually grip the minerals and lift them up into the robot. The advantage of this is that during the entire intake process, the minerals are in contact with both wheels, which gives us maximum control. In addition, the grippiness of the silicone works well with both balls and cubes, and they can conform to the different shapes and sizes of the minerals. So now I'll walk you through the process by which we manufactured these wheels. The wheels were entirely custom made, so we didn't buy them from anywhere, and we came up with the design and the process ourselves. It all starts out in CAD, where the wheels are designed on the computer, and then we 3D print this mold. Basically, we want to make it as weak as possible because the mold actually has to be broken apart to take out the wheels. So that means that the finished 3D printed model is actually mostly hollow. Okay, the next step is to measure the volume of the molds by pouring in water and then marking that off on the container. After that, we pour in the base, which is actually what becomes the silicone rubber, and we also dye them at this stage in the process. Next step is to add the catalyst in the 10:1 base to catalyst ratio by weight. This step actually kicks off the reaction of solidifying the silicone. So it starts off as a liquid, but when you mix this chemical in, it starts solidifying.
I'm confused why you made a mold versus just making the wheels in the printer. Is it because you needed to be silicone?
It's because the printer actually cannot handle silicone.
Oh, you chose silicone for its properties?
Yes, silicone has a variety of special properties. It's nice and grippy, and it's pretty flexible, which is really important for a robot because the minerals are different shapes and sizes.
We experimented with printing other flexible materials, but they were not nearly as grippy and flexible as this.
Oh, it's very clever to step back and say, make a mold from the printer and then produce the thing you want.
It gives us a lot of control over the manufacturing process.
Question for you. You can go back one more slide, please. Now, how did you come up with the catalyst base ratio 10:1?
This was actually, we didn't come up with this. We bought the silicone and it had a base and catalyst and it said.
Okay, so you have okay.
Yeah.
So the recipe came with it.
Yes. One second. Yeah. Okay. The next step is to pour the mixture into a mold. We do this in small amounts at a time because we don't want it to overflow. This stage of the process is actually pretty critical to the entire process because it drastically increases the strength of the finished parts. Whenever you're pouring in the silicone into the mold, it often introduces a lot of air bubbles. So we use a vacuum chamber to pull those out of the silicone. The important thing is that this increases the strength a lot because in the finished product, then we don't have tiny air pockets that would decrease the strength. When that's done and all the silicone is poured into the mold and all the bubbles are extracted, we let it cure for 24 hours, and then we break open the mold to extract the wheel, as you can see here. We went through 3 iterations of the wheel design throughout the season. This was version 1. It was more of a test of the molding process and the properties of the material than an actual prototype. We did come up with the 4-bladed design here, but the blades tended to spin out under centrifugal force when the wheel was rotated, and they could fold in on themselves, and the wheel as a whole was too squishy. So that's version 2, which is the second iteration of our design. These are the ones that we were able to make into our first viable prototype. So you actually attach them to a driving mechanism, as you can see here. We had several improvements over the first version. So in each blade, if you look at the wheel, you can see there's an additional rib over version 1 in the middle there. This is to improve stiffness and prevent them from folding in on themselves. The spikes on the surface of the wheel are also more spiky. This helps out with picking out the minerals. There were still a couple of problems, which is that the blades tended to fly out under centrifugal force. But cubes worked flawlessly. And then finally, there was another problem with balls, which you can see here, which is that they tended to roll against each other and away from the surface of the wheels. We tested this out by filming the mechanism in slow motion, actually, and we noticed this problem, which we solved in version 3. So this is our third version of the wheels, which is what we use in our robot currently. Since we're still using silicone, the wheels are nice and flexible, and they have spikes again to work well with balls and cubes. We used curved arms instead of wheels in this iteration, which help to pull the balls in, and they can't roll against the surface of the wheel anymore. We also dyed it blue to match the colors of our team, and the driving mechanism was twice as fast as the previous version. Okay, so now I'm going to talk about the driving mechanism. So there are a couple constraints on our design. First of all, the wheels had to spin in opposite directions, and they have to be far apart to pick up the minerals. So in order to solve this, we came up with a mechanism that involves a horizontal drive shaft that's common to both wheels. Then there's a bevel gear system on each side. These apply a 2-to-1 ratio, which increases speed, and it also converts the horizontal rotation into vertical rotation of the wheels. So our first version of this design used this core hex motor, as you can see here. It has a unique mounting mechanism, which allowed it to be mounted horizontally like this, which actually worked out really well for our design. And it was nice and light because these motors that are lifting out the mechanism aren't that strong. There were a couple of problems with this, primarily that the motor was weak and also pretty slow. So that's why we upgraded to our second version, which uses this Neverest Orbital 20 motor, as you can see here. It's twice as fast as the core hex motor. It's a lot stronger, but it's also heavier and requires a chain drive, which you can see here. We'll demo the collection wheels on the robot.
Spinning, and it drives over.
that. Right, so now we're going to talk about the extension mechanisms, which you saw right here and right here. So we use these mechanisms to extend quickly and where the robot couldn't necessarily go as efficiently or fast. So we string both of the mechanisms, and we use two different kinds of stringing. One is continuous stringing right here, and the other is cascading. So the main difference between them is that continuous uses one string which goes throughout all of the stages of the mechanism, and it brings up the platform, but the stages move at different, they don't move at the same time. And at cascading, there's one string for each stage. So when you pull the bottom string, all of the stages move at the same time. So that makes it a lot faster, and there's more of a mechanical advantage, but it's also lower torque. So the drawer slides, which you just saw, to extend into the crater, this is what a drawer slide is. It's the slides on a drawer. Oh. So we use this because when they're vertical, they're very strong. So even if we have a weight at the end, they will not bend. And we use two drawer slides bolted together for maximum extension into the crater. So we can get all the minerals at the very end. And then we use two phone cords, which hold all the necessary servo wires, motor wires, and sensor wires for the collection. And then we string this continuously because we're not necessarily as worried about being fast here. We want it to go out consistently, and we are more worried about torque.
So do you have any, I know you talked about torque a couple of times. So what is the maximum weight that thing can handle? Because it has low torque.
We haven't tested it with weight, but we originally string this with the other kind of stringing, which is not as torque, and it would slow down very much when it got to the end. So for this, we wanted to go maximum extension, and this goes a little bit slower, but it goes all the way out. So this is powered by a motor in the back of the robot, which has a quadruple spool with 4 strings coming out of it, which power the extension and retraction of the drawer slides. So these 2 strings power the extension on either side. So when those go in, the drawer slides go out. And at the same time as the extension strings are pulled in, the retraction strings are let out. So, and then when we want to retract the collection, these strings go back in. This makes it all very consistent and reliable, and all the strings are kept taut, and they go in and out the same every single time. So once the strings...
How does it know when it reaches the most extent, when the arm extends all the way to the end?
So
when do you stop it?
We have sensors on the robot.
Okay.
They're called Hall effect sensors, and they sense when a magnet is, so when a magnet is there. So we have magnets on the drawer slides, and when it's all the way out, the sensor senses that, so it stops the motor. So once the strings come out from the motor, they're fed through a series of bearings, which direct the strings to the front of the robot, where then they are connected to more bearings on the drawer slides and strung in such a way so when it's pulled, the drawer slides move out. And then for retraction, we connect the other string to the front of collection so that when we pull the retraction string, it just pulls the collection back. So now we're going to talk about the scoring mechanism, which brings the cubes up and deposits them into the lander. So for this, we use 4 consecutive X-rails strung in a double cascading manner, and it's powered both up and down. So it's very fast, frictionless, and reliable because of the X-rails. They have bearings on them, so they're very fast. Yeah. One of the cons of it is the bearings, if they're not tightened perfectly, they can be a bit loose and wobbly, but in the end it works very well. So this is powered by a double spool right here, which is very similar to the quadruple spool before. It has one string that, when pulled, brings all the X-rails up, and one which pulls it back down. And
as you can see, this just looks like a mess of strings. And so it was strung in cascading up and down, which was very hard to visualize because we needed 2 strings for each stage. But it worked very well in the end because of how fast it was. And we needed to string it in the reverse direction to power it down because it would not be fast enough going down with just gravity pulling it down. We needed to pull it down physically. As you can see, the box, when it goes all the way up, there needs to be a servo on that box to open and close, so we need to get a wire all the way up there. And at first we tried things like the phone cord, which we used on the drawer slides, but that wasn't working very well because when we went all the way up, the phone cord would be taut and it would be pulling back down, and the motor wasn't powerful enough to do that. So we discovered this method of stringing the wire so that it maintained a constant length through the X-rails, and it was never pulling down, and it was very organized at the bottom. So previously, we also tried using 2 sets of these X-rails on either side of a box. That's because at that time the box was a lot bigger and bulkier, and then we realized that if we made the box lighter and heavy, that we would only use 1 X-rail, and that opened up a lot more space for us to use. And we also tried using these Rev Slides, which are a lot smaller. And we were worried about space, so that seemed like a good idea. But there was also a lot more friction in these than the X-rails.
So now that we have the minerals, we actually need to score them into the lander. So we had multiple iterations of this process. Our first iteration involved a flipping-based box, which took 2 minerals that were parallel and flipped them into the lander. So one of the biggest problems we faced with the lander is actually getting the minerals into different compartments, and this idea did not really help. This idea was really easy to build and was quick in terms of depositing, but its biggest disadvantage is because it can only support one kind of mineral because it supports one kind of compartment. It meant that you just had to drive around for the balls and prefer for the cubes and prefer the balls that are actually multiplied, and the cubes who are abundant we had to drive a lot, so it really wasn't working. This is our first scoring box iteration. This is the cardboard version of it. So it was made to fit the original collection mechanism, which was the noodler, which Anhan talked about earlier. So it had one of its major problems was actually transferring from the noodler to the box. So this box, because the minerals were stored parallel, it meant that the noodler would often just hit the minerals back into the same place, and then we would just stand there and wait for the minerals to randomly change direction, which was just very time-consuming. And this was later we made with Lexan, but it had the same problems. It was very similar. So we need to come up with a new idea. So one of the first things we noticed was that the balls and cubes are in slightly different sizes. The balls are slightly bigger, which we didn't think was a major factor, but we realized later that it can be used to actually sort them. So what we did was design a mechanism that would go automatically into the compartment of the cubes, but all the balls, because they were bigger, would drag them over into the other one, which was the gravity sorting. So this is an example of one of the first 3D printed versions of the gravity sorting.
Could you show how that works with the actual?
Yeah, so I can show that on the actual thing too, but balls in the same way, cubes go inside, which allows them, especially when there's like small regions to.
Sorry, actual mechanism. The gate open. Balls go to the side. Cubes.
When you have to score into 2 very close compartments, and since there's like triangles there, it sorts them. Okay, so this saved us a lot of time, and because it didn't require us to constantly move, which was one of the biggest issues in driving. It made drivers have to work significantly just less hard. And but one of the biggest disadvantages with this is that it was sequential, which meant that in the beginning we faced a lot of friction problems, and the balls had to fall, which meant we have to wait a bit. But as you can see now, it's very quick because we have So this is our second iteration of the scoring box. This was designed in CAD, but it was later fully remade out of Lexington and was made by hand. So one of the biggest disadvantages of this box is, as you can see, there are two sets of holes here. So these holes both were connected to servos, and the servos constantly flip the box in order to score. And this box is really heavy, so it didn't work well and killed servos, so not fun. So while it was an improvement in design because it saved time, the flipping had to leave. It just wasn't a good idea. So this is our final iteration. So this iteration uses a door which is controlled by a 4-bar linkage. So you can see this door over here is controlled by a servo which is under it. So this 4-bar linkage just opens and closes the servo, which means that the servo doesn't take space like as much as it would, which allows us to have the box tilted down at all times. So the 4-bar linkage is detailed in that image over there. It's called a 4-bar linkage because there are 3 bars moving the servo and then an invisible bar, kind of bar. And it's just things.
Okay, so next we're going to be talking about the hanging mechanism. So basically at the start of the match, the robot is actually latched onto the lander and it has to lower itself onto the ground. And at the end of each match, the robot has to latch itself back onto the lander and lift itself off. Alright, so for our original design, we had a servo which turned a foam wheel and that would push an axle to open and close the latch. The disadvantages to this were that it was slow and not very reliable because the foam wheel didn't have much of a grip on the axle and the drivers also couldn't exactly see what they were doing, so they often didn't know whether it was closed or open. Okay, so to actually extend the hanging mechanism and latch the robot onto the lander, we could either use a rack and pinion or a lead screw. So for the rack and pinion, it had a low mechanical advantage. It was easy to backdrive, and it would often get jammed because there were multiple segments of the rack that we had to use in order to get the height that we wanted. But the one advantage was that it was relatively fast. For the lead screw, it had a high mechanical advantage and it was difficult to backdrive. But the disadvantage was that it was slower than. Okay, so to actually latch the robot onto the lander, we used the custom machine metal, and they were spring-loaded, so they could only open to let the lander hook pass through in one direction. And so what was good about this was that there was lots of room for error. So the latch didn't have to line up perfectly with the hook on the lander in order to have a successful hang. But we ended up not using the latches in the final design because they actually took up too much space. So they were too tall. So in order for the hang to be valid, the robot had to be over 4 inches above the ground. And the problem with the latches was that it caused the robot to tilt too much. So that the bottom would be the back wheels would be less than 4 inches above the ground. And by using just a simple hook, although it was there was less room for error, it might take longer time, it reduced the height of the robot so that it was above 4 inches off the ground and we would have a valid hang.
We utilize a lot of CAD and milling and printing in this robot, as you can see. CAD is computer-aided design, and we use it for custom milling, printing, and prototyping the material over time. So this allows us to pre-plan a lot of what we do and actually just build things beforehand. Like this whole collection mechanism, for example, was prototyped in CAD. And the robot itself contains many 3D printed pieces. You can see like this, we just use it we use it a lot because it's just really nice for customizability, versatility, and just it can fit anywhere. 4 parts of the robot were fully prototype designed and planned in CAD, which include the collection wheels, the drivetrain plates here, the whole collection mechanism in the box. We also have a milling machine, which is our CNC that we have for the school. Is Cardboard 3D Nomad 83. So it's just a CNC allows us to cut materials with really high precision, especially metal. We can buy aluminum plates to cut or wood for prototyping. CAD software we use, Fusion 360, supports testing and just exporting for.
These devices, are they part of the high school curriculum, or are they just?
These are just not part of the high school curriculum, but they are part of the makerspace, which we use. So these devices can be taught in school, but we have to learn about them ourselves. We have to find out everything by ourselves, and learning is a large part of it. Okay, so Fusion 360. So this year we transitioned from SolidWorks to Fusion 360. So why did we choose Fusion 360? So it's a lot easier to learn, and its biggest advantage is that it's saved on the cloud automatically, so it was easier to collaborate with people, which meant last year there was a lot of yelling involved on people that didn't upload, and then they forced me to upload, and then, yeah, it wasn't fun. It just wasn't fun. So Fusion is available to the whole team. It's free to download, and it has some disadvantages, especially because so many of the people got used to SolidWorks, and just multiple things were different, like the joints, and it was slightly different, but overall it has its advantages, and there outweighed disadvantages, so making the switch was definitely worth it. Fusion 360 it's a CAD software. It's a software that allows us to plan everything online to make 3D models. And
do you still put a little SolidWorks into your training? Because SolidWorks is more the industry standard.
Yeah, because it was just easier to shift the whole thing towards Fusion, we made a full shift. We no longer use SolidWorks despite it being standard. Mainly because we only have limited copies of SolidWorks that are free for us. So giving it to everyone was just not very practical because we didn't have enough. So that's the main things that forced the switch.
Do you have the ability to transfer files from SolidWorks to Fusion and vice versa?
We do, but as we transfer them, a lot of the information there is just modified or lost. So we do it just for general things.
So the files that you create from Fusion 360, is that the one you send down to the 3D printer?
Yeah, all files from both of them can be sent to the 3D printer. The 3D printer just takes a file which it converts to an STL and just prints it.
Is that in DXF format, or what kind of format?
The format that the 3D printer accepts is so the CAD software exports an STL, which is STL is it's a bunch of triangles that just details the whole print, and then each printer has its own software. And for example, MakerBot that we often use has its MakerBot software that turns the STL into something more usable. So we can actually print. So I'm just going to talk a bit about the models that are on the robot that I 3D printed or milled. So Anhad earlier talked about the collection wheels, which were fully 3D printed. I'm going to add on to that drivetrain plates. So he talked a bit about the elevated drivetrain, and it's fully milled in how it was designed. So there are plates here and here, which connect this to the Tetrix chassis, which means that which just makes the elevator design significantly easier to make because we didn't have to deal with something that doesn't really exist. So it was made in Fusion. It was fully milled in RCNC. Actually, no, yeah, it was Formulatrix. One of our people. It was designed by us. Right? It was we started milling in RCNC, but then we moved on to an industrial CNC at Formulatrix because we didn't have the resources to mill it. So I talked about how this was fully designed in CAD. So we use a kit of parts mainly called Tetrix that we've used over previous years. And another kit of part exists called Octobotics. Octobotics is different. It has its advantages, it has its disadvantages, and it can be made with these X-rail that can be lighter if you use them correctly. So in order to know what we want to buy for this prototype, we fully planned and designed the collection system in CAD, and then we just knew what to buy, and then we just bought the parts ahead of time from what we knew we needed and assembled it. So that just saved us mainly a bunch of money and time even, because we have limited time in the robotics room. So.
Were you able to do a simulation in the Fusion 360?
So Actobotix, Tetrix, and most of these big companies produce like step files, which are just 3D models of all their parts, and we can make assemblies with them, which allows us to test things in CAD. So all of it can be done in the software. So also the scoring box, as you can see, is mostly 3D printed. There is this Lexan piece that was later. And this scoring box is, it allowed us to face a lot of space constraints. So the one you saw earlier, which is there right now, did not work because of the space constraints. And by printing it allowed us to just make sure it fits in the robot and provide customizability and versatility and things like the 4-bar linkage. So also the whole robot is imported to CAD, you can see here. So by exporting the whole robot to CAD, we can actually test a lot of the mechanisms. So we tested the scoring box and the collection mechanism before actually, to make sure they fit in terms of space, before actually putting them. So we knew that everything we had fit in the 18-inch requirement. So that made our life easier for the builders. And while the building process was very hands-on, and we built it in we worked on building it with our hands, we imported it to CAD later so we can actually test things in it that are more complex.
So actually to make hardware work, we need some software. So for our robot, to program it, we use Java, and we use Android Studio as our IDE. So this is for controlling the movement. We utilize this. Can I show the controller? To utilize these controllers, because we have holonomic Drivetrain, we need we can utilize 2 sticks in order to move our robot. So the one would control moving forward and sideways, and the other would control rotation.
How much does the robot currently weigh?
Just under 42 pounds.
42 pounds?
Limit. Yeah. A lot of the major weight comes from the CNC parts because they're really thick aluminum, like the drivetrain plates. So all that's actually new rules. Yeah, that is because of the engine mainly. So you can forward, backward, side. Good example of the mechanism.
You run down the aisle, maybe? Everybody can. Exactly.
One heck of a video game.
So, as you saw in the demonstration video, the first part of the match is completely autonomous. So we need to pre-program our robot. We don't use nobody's controlling robot during this period. So we have several objectives. So we start hanging on the lander here. So we need to unlatch, and then here. So these minerals would be positioned here. One of them would be gold, and other would be 2 silvers. So they would be positioned like this.
So the balls are actually on the ground?
Yes. Okay. So our objective is we utilize our phone camera to identify the position of gold mineral, and then we need to to move the gold mineral without moving silver minerals. Then we need to go to the depot here and place our T marker, which is this thing here, and then we need to go to the crater and partially be inside of it. Also, during this autonomous, we use several sensors. So we use whole sensors, so there are magnetic limit switches So we use them like to determine where are the limits for the hanging. And we also use motor encoders in order like to understand how many rotations did motor make, so we can estimate our distance traveled. And also we use color sensor, which is located here, to see if we're able to score the gold mineral.
Yeah. All of our robot movements are done with encoders. So the idea is that can you go back one? So when we drive off, we can specify distances you want the robot to drive and angles, and then from there we can add logic in order to make this path work. So
we'll use the gyroscope to understand how.
Right. So the one really key sensor we have is the gyroscope. So within this control hub that we have over here, the phone talks to it. It has a 9-axis gyroscope, and we mainly use it for our yaw. So we can make really accurate turns using like a controller, which tries to maintain a good heading from the hub. So we utilize the phone's camera. Our phone's right here, and our hanging latch is back here. So as we're dropping, we're able to utilize the camera to see the minerals right in front of us. So there's kind of like 3 steps that go into computer vision. The first one's to parse the image for the color yellow in order to find the cube, store the contour, and compare it with previously known positions. So that's like a really high level. The idea of parsing the image is that we can take the image, and we know these gold cubes are yellow, and they tend to contrast against the background. So we can apply things like color filters and try experimenting in different color spaces in order to see what kind of constraints can we put on our image in order to find the color yellow. And then from there, once we have these like blobs of yellowish contours, we can figure out which one is most likely the cube. So this is done using like area, height to width ratio, like kind of common sense ideas.
So here is the picture of what our robot sees. So as you can see, the image is divided into 3 sectors. So one is like for each mineral, and you can see like it is able to correctly identify the gold mineral. And light blue indicates potential silver, but because like the silver is much less contrast with the backgrounds, it's reliable. So you also see like it detects silver here and here, which actually is not a silver.
We were having problems with shadows, as you can see over here. So like the tiles are gray, and like white is effectively a shade of gray. So depending on how much light or where the light was coming from, you can see that it started missing things, and then it started catching the floor too. So it was pretty unreliable. But you can see on the left over here, the gold filter was much more robustly tuned. So it was much better, and it did not deceive us. So while motor encoders are pretty good, they do have their drawbacks. Namely, the idea is like, if we're just in an environment by ourselves, we can encode these values, and ideally the program will work correctly. But we may face problems such as slippage, like if our robot's driving really fast in one direction, and then we sharply just turn the motors to a different direction, we still have a little bit of momentum in that original direction. So these kind of errors tend to add up, and then like one really big obvious error would be like if you're driving and then your partner accidentally slams into you, there's no really good way to tell by your motor encoders if something's gone wrong, especially with Mechanism because they have their own free axis. So they may slip on the rollers. So yeah, here's a video. You'll see our robots right in the top. So one of our special parts of our autonomous is that we try to score a cube that we collect. And you can see that as it deposits, it's right on the edge. And what happens there is that as the robot's backing into the lander, it actually hits one of these lander legs, and it just happened to be that it started rotating, and it almost didn't make the mark there. Yeah. So the ideal solution to this is that if we have some passive tracking system on our robot, we would be able to like actively correct for the error given our robot pose. This is the idea of tracking wheels. There are 3 different encoders. The idea of Omni Wheels is that they have a measured axis and then a free axis because they have these rubber rollers on them, kind of like so.
So the beauty of it is that we can place this on an area, we can drive a little bit, and it will measure our movement component in one axis. For example, this one is moving forward, so we're able to measure the distance and move forward. And this one is pointed 90 degrees, so we can measure our movement in the x-axis. Yeah, so this would be like an ideal version 2 of what you'll see over there. And they're basically just Omni Wheels, so they're passive encoders that are placed on a linear bearing. And then from there, we can track distance in one direction. The reason why we need linear bearings such as this is because our ground is not always even. So while we do have like foam tiles, sometimes they may sink, the wheels may sink a little bit too much, and the worst thing would be that if your robot ends up, if the Omni Wheels are too low, then it may like bring your actual wheels up and then you can't drive your robot. So it's very important to have them spring-loaded in some way so they maintain contact with the ground, but the drivetrain wheels comes first. If you have 3 correctly placed tracking wheels, we can actually do some math in order to figure out where our robot is on the field. So you can see that when we move in the x-axis, only this 90-degree encoder will actually read. And then when we move in let's say y-axis, our robot will only read with these 2 encoders. And then when we rotate, the 2 encoders, this one and this one, will move in different amounts because they're in different areas, and they'll move in different directions. So from there, we can figure out our rotation. If we have these x, y, and rotation values, we can apply an active algorithm, which we call pure pursuit. So the idea really generally, you first apply a path. So in this example, it's this really, really, really faint line, which goes from here to here. And here's our robot right here. So the idea is that the robot wants to eventually get to here, but it's not on the line right now. So one solution may be to just kind of go to the line, stop, and then turn, and then follow down the line as usual. But the reality is that there always will be just errors because we can never be perfectly straight. Something may happen, and we want to actively correct for it. Another constraint we have is that we want to make our robot really fast. So since this robot drives fastest when it goes forward, we want to apply kind of like an Ackermann steering. The idea is that kind of like how a car drives in a circle, we want to also drive in circles from where we are. So what pure pursuit does is that it takes our robot current position, it picks some arbitrary number, which is its radius. And the idea is that it's always trying to go towards the intersection of this circle and its path. And at every point, it tries to find the circle that matches it. And the only 3 constraints are that it's tangent to its current position, so it can turn to it. It goes through the original point, and it goes through this target point, which is computed by intersecting our circle with the line. Okay, so since it's kind of confusing, we have a nice little demo for you. So over here you can see this is the robot and it's going over this path. So at every point it kind of snaps on by calculating that target point, and then it keeps kind of turning towards it. So you can see that it's taken a really blocky path and started to smoothen it out. But while it does work well on things like this semicircle over here where it's virtually circular, it still does have its drawbacks. For example, these sharp edges over here, it kind of cuts right through them. So it is a really nice algorithm, but it does have its problems too. Another thing is just about controlling mechanisms. So the reality is that on this robot, there are only 2 drivers and there are more than 2 mechanisms. The key to having a faster robot is to have interconnected mechanisms and to make them more automatic. We implement safeguards in our robot in order to prevent the driver from doing things that may harm the robot. For example, if this collection is all the way down, like this, and the robot's retracting, then we know that the servos are going to start hurting themselves because they're going to eventually hit this crossbar right here. So we don't want that to happen. So a lot of these mechanisms that require specific positions need to have nice transition states to go from one to another. Our solution to this is kind of commonly known as finite state machines. So the idea is that we describe a bunch of states we want the robot to be in, and then we can indicate with arrows or like kind of like a graph, we can indicate how to go between them. So on our robot, we have like 5 different actual controllable mechanisms. For example, our extension for our scoring box, the actual box servo, the extension on collection, the collection angle, and the hanging. So in this example, I kind of just mimicked it over here. The extension's all the way up, the box is open. The extension on collection is fully retracted. The collection angle's in the middle, and the hanging is all the way down. So that's one example of a state in our finite state machine. Another one could be the box is fully closed, the extension's all the way retracted, but this collection's all the way out, and it's currently actively collecting. Once we have our different states, we can kind of put them together like this, and it kind of shows how we're able to kind of automate different parts and implement safeguards. So this would be like our collection finite state machine. Start from actually over here where collection's retracted, the position's in the middle, and then as we press A, it goes directly to collection extended, position down. And this is because when we're fully in, we know the servos can't turn fast enough to actually hurt themselves. And since the spool works faster than the servos, we know we'll be safe. But as we go back, we need to make sure that we don't accidentally hit the box with our crossbar. So we implement these intermediate steps that the robot does before it eventually returns back to the retracted position. In order to go between these different states, this is where we use our sensors, and they kind of come key because we want to make sure that we don't accidentally dump too early, so we can't rely on time. So these transitions are automatic, utilize our sensors, and that's the kind of the key to making our robot extremely fast and extremely easy. So you can see this really, really integral piece of our robot is actually only controlled by two buttons, namely A and B. B retracts it, A extends it forward. And the key to this, or the upshot of this, is that now the driver can focus more on positioning the robot to collect minerals instead of worrying about whether mechanisms work.
So we've talked a lot about the technical skills that we've learned throughout the year. However, we also learn a lot about other skills that we should know in life. The first one is communication. We have a 15-member team. This isn't even all of us. And we all work on different parts of the robot. And so it's really important that we all know how to communicate our ideas and goals and deadlines throughout the season. The next thing is goal setting. We have a 7-month season, and we try to set long-range goals and then break them up into smaller tasks that we can keep track of. The last thing is collaboration. We, again, have 15 members, and so we kick off every year with a sticky note meeting where everybody brainstorms different solutions to the challenge that we've been given. We decide on the path forward through different meetings with everyone where we weigh the pros and cons of all the ideas that we have.
So there were about 8 seniors during this season, including myself, and we'll all be going to college this fall to study a STEM-related field, whether that be biology, chemistry, mechanical engineering, electrical engineering, computer science. We'll all be studying what we really want to study in college, which is very respectable, in my opinion. So I chose to do mechanical engineering at NYU starting this fall, and I'm possibly a minor in computer science and electrical engineering, which I'm very, very excited for. So other than NYU, other schools that this year's seniors are going to attend are UIUC, Purdue, UMass, RPI, and Northeastern. So throughout high school, I was involved with Robotics Club. However, I was also involved with different clubs and organizations such as K-pop dance crew, there's me dancing during the concert, and I was also involved with the school newspaper club. So I was able to talk with my friends and peers in different diverse groups of people and talk about what we want to do after college, after high school. And the one thing that I've noticed that's really special about people inside the Robotics Club is that they know what they want to do after high school, which is a very huge privilege to have. And the club allows oneself to find what they really want to study further and what their passion is by allowing the students to be exposed and really experience what different kinds of engineerings. For example, 2% of Byte does a wonderful job of giving everyone a chance to work mechanical aspects, electrical aspects, and computer science. And even though I'll be going to college and all my peers will be going to college, so we have not cut ties with the team So there's an alumni day annually where all the previous 2% of Byte members come back for a day to socialize and see how the team is doing. And whenever the team hosts a qualifier, the alumni also volunteer at these events to help out the team in any way because the team has helped them so much. So that's the end of the show.
Thank you, 9/15 of 2 bits and a byte.
We're done? Yeah. I think it's done. Okay.
So hi, here. Wait, where is shear? Sheared right here.
Yes.